Well, hello there, good people. Today we are talking about thermal energy and friends. And by that we mean we're going to talk about thermal energy and then other related definitions to thermal energy. Why is this doing this? Don't do that. Okay, there we go. Today we are starting a brand new unit on thermodynamics. And when we start this brand new unit, we are going to start this unit just by learning a lot of vocab terms. These vocab terms will be ones that come up again and again and again. They're going to be little nuances and distinctions between these vocab terms. They seem like really, really similar concepts, but what you'll see as we get into them is that they do have, oh, wow, unused printers. That is fun. We'll see that there are some distinctions between these vocab words, and so we're going to take a look at those today. And today I do have for you a slideshow. Today we are talking about thermal energy and other related concepts. And this is probably going to load eventually. Perfect. Okay, can I go to the next slide, please? Yes, I can. Our first vocab word for today is thermal energy. But before we talk about energy, before we talk about thermal energy, let's talk about what energy is. You'll remember that energy is the ability to do work. We already know a few different types of energy, like potential energy or kinetic energy. But today we're going to talk about another category of energy. So thermal energy is a category of energy, just like potential or kinetic energy. And this is energy contained in a substance due to the total particle kinetic energy. When we're talking about thermal energy, where's my pens? Hello, pens? Oh gosh, I have no pens. Okay, well, oh my. See if I can get pens back. This is taking way too long. I'm going to keep talking while this loads. Thermal energy is energy contained in a substance due to the total particle kinetic energy. Please underline the word total there. Due to the total particle kinetic energy. When we're talking about the particle kinetic energy, we know, and you learned this in chemistry, that particles are moving all the time. They're always kind of zippy zapping all over the place. And so when you have an object that's just sitting there, it is just sitting there, but inside the atoms and the molecules are very, very quick at work. They're moving around a lot. We call that Brownian motion, which is the random, chaotic, and haphazard molecular motion of the particles in a substance. I said, i.e. molecular moshing, as all of the little molecules just kind of bounce around. We know, or you know from your chemistry class or from days of old or your times in physical science or your times in elementary school, that we have Brownian motion for particles in a liquid or a gas. In a liquid or a gas, they move a little bit quicker, and then in a solid, they kind of vibrate about more or less fixed positions, but are still in constant motion. So when we're talking about thermal energy, we're talking about the total energy that a substance has because, don't end the recording, just move this up. We're talking about the total energy that a substance has because of those little molecules just kind of moving around haphazardly and chaotically. If you had 7 little molecules that were all moving around, you would take their total kinetic energy. So you would add together the kinetic energy of each particle to find the thermal energy of the object. If you had 14 particles, then you would add together the kinetic energy for each of those little particles, so you would have twice as much thermal energy. So we see that thermal energy doesn't just depend on how fast they're moving, although it does depend on how fast they're moving, and it depends on the kinetic energy of each particle, but it also depends on how many particles there are. If you have more molecules that are moving, you just have more thermal energy. Next, our next type of energy that we're going to be talking about today is internal energy. Internal energy is the total energy in a substance due to thermal energy, molecular chemical potential energy, and mass energy. Here's the thing about internal energy. Internal energy is another category of energy, just like how you would have potential energy or kinetic energy. We say, if I were to make a little tree of energy here, in my energy tree, and this pen is crazy, so we'll see how it does. It makes everything really angly. Okay, in my energy tree, there are lots of different types of energies. One type of energy is what we call mechanical energy. And this is the type of energy that we have dealt with so far this semester. Mechanical energy includes kinetic energy and potential energy. That looks like a V, but it is, in fact, a U. There's also another type of energy, and that energy is called internal energy. Internal energy has to do with all of the energy of the little molecules that are inside of a substance. So when we're talking about mechanical energy, that's like how fast is the object moving and where is it located with respect to the earth? Is it on a spring? That kind of thing. So mechanical energy has to do with how fast the object is moving and how much potential energy it has. Internal energy is how much energy that object actually has inside of it due to what's happening with the molecules. So that includes thermal energy, which we just discussed. Thermal energy is due to the motion of the molecules inside of the substance. It also includes chemical potential energy. Chemical potential energy, except that doesn't look like an M. Chemical potential. That's like if you had a lot of energy stored in bonds between the molecules, that would be part of internal energy. And then the last one that we have is mass energy. We will talk way more about mass energy when we get to Unit 12. Mass energy is the energy that you get from Einstein's famous equation equals mc squared, and it says that mass can actually be turned into energy. So, internal energy is the total energy that an object has kind of inside of the object because of the interactions or the movement of the molecules inside of the object. So we just talked about thermal energy. Thermal energy is a subcategory of internal energy. Quick little checkpoint, check in with yourself. Can you tell what's the difference between mechanical energy and internal energy? And then what's the difference between internal energy and thermal energy? Take a quick check with yourself, make sure that makes sense to you. Okay, how do I clear this? Clear. Ciao. Next, we're going to talk about temperature. Temperature is a relative measure of the average kinetic energy, do underline the word average, kinetic energy of all of the particles in a substance. Temperature is not the same thing as thermal energy, and we'll talk about units in a second. It's measured in degrees Fahrenheit, degrees Celsius, or kelvins. Temperature is a relative measure of the average kinetic energy of the particles in a substance. Thermal energy, you'll remember, is the total kinetic energy of all of the particles within a substance. So if you have lots of particles moving around very fast and you add together all of their kinetic energies, then you get the total thermal energy of an object. But if you wanted the temperature of an object, what we're looking at is how fast or how much kinetic energy does a particle have on average. If I asked you who has more energy, just like from like kind of an instinctual definition of energy. If I asked you who has more energy, 100 kindergartners sleeping or 5 kindergartners running around on the playground, you would say, well, what do you mean by who has more energy? You would say probably, actually, the 100 kindergartners sleeping they probably have more energy just because there are more of them. You have 100 kindergartners. But if you have 5 kindergartners running on a playground, then each individual kindergartner probably has more energy on average than an average kindergartner who's sleeping. This is the difference between thermal energy and temperature. Temperature is about the average kinetic energy of the particles in a substance. Thermal energy is about the total kinetic energy. When you think about something as being hot, if you touch it and you say, wow, that's hot, you're probably not thinking about the total thermal energy. What you're thinking about is how fast those little particles are moving on average. Something might have a lot of thermal energy just because it's really big. But if it's going to burn you, it has to be because it has a very, very high temperature. Let's take a look at a few examples. If I had a bowl of soup sitting here and 2 bowls of soup sitting here, they would have the same temperature. Let's say that they both have a temperature of 90 degrees Celsius. They both have the same temperature. They both have the same average kinetic energy, but my 2 bowls of soup has twice as much thermal energy as 1 bowl of soup because there are twice as many molecules. So the total is twice as much. If I had an iceberg and a cup of hot coffee, my cup of hot coffee would have a higher temperature. The kinetic energy of the particles in the coffee on average would be greater than the kinetic energy of the particles in the iceberg. But my iceberg would actually probably have more, most definitely have more thermal energy. Why? Because icebergs are huge and a cup of coffee is relatively small. So even though all of those particles are moving really slowly in an iceberg, there are just so many more of them that you would have way more thermal energy in the iceberg than you would have in a cup of coffee. This is the difference. If I asked you which has more thermal energy, a cup of hot coffee or a cup of gasoline, you would say that a cup of hot coffee has more thermal energy. But the cup of gasoline probably has more internal energy. That's because the cup of hot coffee has more temperature. It has a greater kinetic energy of the particles on average, and so it has a greater thermal energy because the particles are moving faster. But the energy that is stored in those bonds inside of gasoline, you have way more chemical potential energy inside of gasoline than you do in a cup of coffee. Gasoline will make an explosion. A cup of coffee probably won't. So there's a difference. Let's talk a little bit about units here. There are 3 units that we can use for temperature: degrees Fahrenheit, degrees Celsius, or kelvins. Let me clear this out here. Let's go purple, because that sounds fun. Okay. Let's talk, actually, I'm going to go back to my other screen here, because that's going to be easier, because I got a lot of things to write. Okay. Dun, 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 dun. You can do it, buddy. You got it. You're super awesome. And I know it's really hard to load sometimes, but you're doing a very great job. Hey. Sorry, I say that. It is doing a great job. Okay, I really do want the color purple. Okay. Okay, here we go. Let's talk about our 3 units of temperature. Why is this still big? Don't be massive, please. Okay. Temperature we can measure in Fahrenheit. We can measure in Celsius. And we can measure in Kelvin. In Fahrenheit, water boils at 212 degrees Fahrenheit. In Celsius, water boils at 100 degrees Celsius. And in Kelvin, water boils at 373 Kelvin. In Fahrenheit, water freezes Okay, W. Nailed it. At 32 degrees Fahrenheit. In Celsius, water freezes at 0 degrees Celsius. And you know that water freezes at 273 Kelvin. So far, can you see how Celsius is a very, very nice unit of measurement of temperature? Here's what Celsius says. Remember, temperature is all about the average kinetic energy of the particles. So here's what Celsius says. Celsius says, okay, let's make things nice and simple here. We'll say that the particles have an average kinetic energy of 100 at the boiling point of water. And we'll say that the particles have an average kinetic energy of 0 at the freezing point of water. And so then Celsius kind of acts as a relative scale. Actually, all of these are relative scales, but they're showing about approximately how warm or how cold something is based on the average kinetic energy of the particles. And for Celsius, it's based off of water, which is very, very nice. For Kelvin, here's the thing. You're looking at these numbers and you say, these numbers are insano, crazy banana pants. Well, that's because Kelvin is based off of the coldest thing possible. Kelvin is based off of the 0 point, which we call absolute zero. Here's what Kelvin is based on. Kelvins are based on the point at which the particles in a substance would have 0 kinetic energy. In other words, 0 Kelvin happens when the particles are not moving at all. If they are completely and totally still, we have 0 Kelvin. So that is the starting point for, or that is the basis for Kelvin. So Celsius is based on water. Kelvins are based on the coldest possible temperature ever, which is absolute 0, the temperature at which no particles are moving at all. In Celsius, absolute 0 happens at negative 273 degrees Celsius. In Fahrenheit, absolute 0 happens at negative 460 degrees Fahrenheit. Now, let's talk about absolute 0 for a quick second, because absolute 0 actually isn't really very possible. We have never gotten something down to 0 degrees Kelvin, or 0 Kelvin. There are no degrees. You'll notice there's no degree symbol here for Kelvin, but there is a degree symbol for Celsius and for Fahrenheit. We've never gotten something down to 0 Kelvin before, because you'd have to get the particles to completely and totally stop moving, and you can't get the particles to completely and totally stop moving. More to come on that when we talk about the laws of thermodynamics. Now, if you want to convert between these guys, we have a few rules that will allow you to convert. Here are some equations for you. We say that the temperature of an object in Fahrenheit, oh gosh, that's embarrassing. Boop. The temperature of an object in Fahrenheit is equal to the temperature of that object in Celsius times 1.8 plus 32 degrees. The temperature of an object in Kelvin is equal to the temperature of that object in degrees Celsius plus 273. Because when an object is at 0 or is at 0 Kelvin, that is negative 273 degrees Celsius is what we have found that the temperature in Celsius that we need to get something to in order for all the particles to stop moving completely. So in order to find the temperature in Kelvin, you add 273. We can use these two equations to convert between each different type of measurement of temperature. Now, suppose that someone said to me, Miss Wilson, you do not want to go outside right now. It is 30 degrees Celsius. Can you check what would 30 degrees Celsius be in Fahrenheit and what would 30 degrees Celsius be in Kelvin? Well, you would say your temperature in Fahrenheit is going to be 1.8 times your temperature in Celsius, which is 30 degrees Celsius, plus 32. Go ahead and plug that into your calculator. I will do that here. And I get that it's 86 degrees. If I wanted to know the temperature that day in Kelvin, I would say, well, that's the temperature that day in degrees Celsius plus 273. So that's going to be, okay, sorry, team. That's going to be 86 degrees Celsius plus 273. And you could do that in your head, but I'm going to use a calculator because I'm like that. It's 359 Kelvin. You could also see if I gave you a temperature in Celsius, or if I gave you a temperature in Fahrenheit, you could convert it to your temperature in Celsius by doing just a little bit of algebra. You'd subtract 32 from both sides and divide both sides by 1.8 to get the temperature in Celsius. In general, I like to think that a normal room temperature in Celsius is something in the 22 to 25 kind of range. So that's kind of how I base my understanding of what's warm and what's cold in Celsius, because Celsius is a little bit unfamiliar to us. Hey, can you guess which one is the SI units? It's Kelvin. Kelvins are the SI units of temperature. Now you say, Ms. Wilson, why would we use Kelvin? And why do scientists prefer it so much? Well, because it actually is based off of 0, which is totally different than Celsius. Here's what's true. 20 degrees Celsius is not 2 times warmer than 10 degrees Celsius. 20 degrees Celsius is not 2 times hotter than 10 degrees Celsius. But 20 Kelvin is 2 times hotter than 10 Kelvin. Here's why. It's because Celsius doesn't really start at 0. Celsius really starts at not the 0 value, it really starts at 273. If I had 293, I would not say that 293 is twice as hot as 283. That's not true. And so Kelvin actually tells you if something is twice as warm as something else. Is if your Kelvins are actually doubled, then it's actually twice as hot. If your Celsius is doubled, that doesn't mean it's twice as hot because Celsius doesn't start at 0. Okay, that's quite a bit on temperature. Let's head on back to our slideshow here. Okay. I think this is all going to work great. Eventually. And then we're going to see our next vocab word. It's going to be super awesome, I believe. Okay, let's move this guy up here like this. And next one. Our next vocab word is heat. Heat is not the same thing as thermal energy. Heat is the thermal energy that is transferred between 2 different substances as a result of differences in temperature. Please underline the word transferred. Heat is the amount of energy that's transferred between 2 substances as a result of differences in temperature. If I take let's say that I take a hot cup of coffee and I put it outside in my car, and I accidentally leave it in my car in the morning, which is a great tragedy, and that hot cup of coffee is now sitting in my very, very cold car. What will happen is thermal energy will leave the cup of coffee and enter into the car. It will cause the car to become slightly warmer, and it will cause the coffee to become slightly cooler. That change, that energy that leaves the coffee, the energy that leaves the coffee and goes into the car, that energy that gets transferred, that's what we call heat. It's the thermal energy that moves between one place and another. It's not, we never say that heat is something that you have, like, for example, in physics, I would not say that this cup of tea has a lot of heat, because heat is always something that you transfer. It's something that's going from one place to another place. So I would say it has a lot of thermal energy, and some of that thermal energy is being transferred. The thermal energy that's being transferred right now to the room, that is what we call heat. Heat will always move from regions of higher temperature to regions of lower temperature. Heat does not go from a place of higher thermal energy to a place of lower thermal energy necessarily. You know this because if you put your hand up against an iceberg actually has more thermal energy than you do. But if you put your hand up against an iceberg, heat will leave your hand and go into the iceberg because it'll go from high temperature to low temperature. It will not go from high thermal energy to low thermal energy. The reason for that is because when we transfer heat, what you're doing is you're just transferring kinetic energy to the particles. So if you have particles that are moving really, really fast, what they'll do is they'll bump into particles that are not moving or moving very, very slowly. When they bump into those particles, they give them a little bit more kinetic energy, and those particles start to move quite a bit quicker. One moment, please. Okay, sorry for that brief interruption. Okay, that wasn't even that brief for you. Okay, no, oh gosh, slide back up. Okay, the last thing that we have to say about heat today is that in physics, we say heat always flows from regions of higher temperature to regions of lower temperature, but we will never talk about how cold moves. We don't talk about how cold moves in physics because cold is not really a thing. Heat is energy that is transferred. You can transfer energy. Cold is really just the absence of energy. Something can have a lot of thermal energy. That means it has a lot of kinetic energy. Something can have, of the particles, something can have very low energy, but it doesn't have cold. It just means it doesn't have as much energy. And so you can't have cold, so we can't transfer cold. You can transfer energy, but you can't transfer the absence of energy. So here's what we say. If I wanted to describe what happens when I take an ice cube and I put it in my coffee, I would say my coffee has a lot of thermal energy and it has a very high temperature. Heat, that thermal energy, will move from my coffee into the ice cube. So I have the transfer of heat from the coffee into the ice cube. The ice cube then will warm up while the coffee cools down. The ice cube warms up because it gains heat. The coffee lost heat, and so it gets cooler. Ice cube gets warmer, and it cools my coffee. Notice the way that I don't talk is I don't say cold moves from the ice cube into the coffee, because cold isn't something that exists as something that can move. So we always talk about the way that energy flows. We never talk about the way that the absence of energy flows. Heat will transfer this way until we reach a state that we call thermal equilibrium. Heat transfer will occur in bodies of different temperature until a common temperature is reached. The two bodies are then said to be in a state that we call thermal equilibrium, and no more heat will flow between them. If I have two objects of different temperatures, let's say the ice cube in my coffee, for example, what will happen is heat will leave the coffee and move into the ice cube, leave the coffee, move into the ice cube, leave the coffee, move into the ice cube, until the ice cube and the coffee are the same temperature. At that point, we say that they are in thermal equilibrium with each other and there won't be a net flow of heat between them. You would never have a coffee that makes an ice cube hotter than the coffee was. And you will never have an ice cube that makes the coffee colder than the ice cube was. Once they reach the same temperature, then the heat transfer will stop and there will be no more flow of heat between them. At this point, we say that they are in thermal equilibrium. Notice you're in thermal equilibrium when they reach the same temperature, not when they reach the same thermal energy. Heat will transfer between you and the iceberg, not until you and the iceberg have the same thermal energy, but until you and the iceberg have the same temperature, which would be really very unfortunate for you and for the polar bears. Anyway, that is pretty much all of our definitions for today. Today we talked about a few definitions. Here's our first one, thermal energy. Thermal energy is a type of internal energy. Thermal energy is due to the kinetic energy of the particles inside of an object. It's the total particle kinetic energy. Internal energy is the energy that an object has because of what's going on with its molecules. So it's the fast moving of the molecules, the potential energy and the bonds between the particles, and mass energy. Temperature is a measure of the average kinetic energy of the particles, not of the total kinetic energy of the particles. That would be thermal energy. Temperature measures the average. We talked about how there are 3 different units for temperature: degrees Fahrenheit, degrees Celsius, and Kelvin. Then we also talked about how to convert between them. Heat is that energy that gets transferred between one substance and another, and that transfer will happen until 2 objects reach a state that we call thermal equilibrium at the same temperature. And that's all for today, folks. I hope you do have a wonderful rest of your day. Bye, good people.